Hello everyone, welcome to the 31st lecture of the course Discrete-time Markov chains and Poisson processes. So, in the last couple of lectures, we learnt about the concept of Poisson thinning and we solved a couple of problems using that concept. So, today we will learn another new property of Poisson process which is about conditional arrival times. So, let us start. So, before starting with the concept, let us first look at an example or a problem. Suppose that you are told that exactly one event of a Poisson process has occurred by time t. So, says this is time t and you were told that in this interval one event has occurred. Now, you are given that information that there has been one event within the time interval 0 to t. Now, the question is that under this information, what is the distribution of the time at which the event occurred? So, you are told that there has been exactly one event in the interval 0 to t, and now under this information you are asked the conditional distribution of the time of occurrence of the event, right. So, that is what this problem is asking you to do. So, let us see how we can solve this. So, basically we are interested in this quantity, right. So, we are interested in the distribution of the time at which the event occurred, and this is one event. So, this is basically the first event. So, we are interested in probability that the time of occurrence of the first event is less than or equal to s, given that there has been exactly one arrival up to time t, right. So, obviously this s should be less than or equal to t, right, because you know that up to time t there has been an arrival. So, the time of arrival or the time of occurrence of the first event should be less than or equal to t. So, if it is s is greater than t, then probability t1. So, if s is greater than t, then probability t1 less than equal to s given nt equal to 1 is just 1, because you are already told that there has been an arrival by time t. So, obviously the time of that arrival should be less than or equal to s if s is greater than t. So, the interesting part is when 0 less than s less than t, that is the interesting part. So, probability t1 less than or equal to s given nt equal to 1. Now, what does that mean? So, this is again a conditional probability. So, we write down the formula of conditional probability. So, this is just probability t1 less than or equal to s intersection nt equal to 1 divided by probability nt equal to 1. Now, you are saying that the first arrival, so if this is s, the first arrival has happened within this time s, right. And you also know that up to time t there has been exactly one arrival. So, combining these two, what we get is that one event in 0 to s and 0 events in this part, open interval s close t, right, because you are saying that there is the first arrival happened within time s and up to time t there has been exactly one arrival. That means there is one event in closed 0 s and 0 events in open s closed t divided by not nt equal to s, but rather it should be nt equal to 1. So, that is a typo. So, it should be probability nt equal to 1. But now, when I write it in this way, these two intervals 0 to s and this interval open s close t, these are disjoint intervals. Poisson process has this property of independent increments. So, events in disjoint intervals are independent. So, you get probability. So, this probability just basically breaks into probability of one event in 0 to s times probability 0 event in S2t, right. So, this is equal to this by independent increments, right, independent increments property, right. Now, one event in 0 to s, that is just lambda s times e to the power minus lambda s, that is the probability of one event in the interval 0 to s, and 0 events in s to t. Again, it has this property of stationary increments. So, the number of events in an interval just depends on the length of the interval. So, that probability is e to the power minus lambda times t minus s, and the denominator is just probability nt equal to 1, which is just lambda t times e to the power minus lambda t. And now, if you do the calculations, do the cancellations, you will see you will get s over t. But this is what is s over t? Remember, we are looking at 0 less than s less than t, and we have already seen that for s greater than t it is 1. So, this is equal to s by t in this regime. So, but that is nothing but the distribution function or the cumulative distribution function of a uniform distribution on the interval 0 to t, right. So, given that there has been one arrival up to time t, the time of that arrival, given that there has been one event up to time t, the time of occurrence of that event will be uniformly distributed on the interval 0 to t. So, if you are told that there has been exactly one event or exactly say one arrival in the interval 0 to t, then under this information, the conditional distribution of that occurrence or time of occurrence of that event or time of arrival is uniformly distributed on the interval 0 to t. That is what we have solved or found out via this problem, right. Now, motivated by this, we come to this theorem, which basically generalizes what we saw in the previous slide. So, given nt equal to n, so now you are told that within time 0 to t there has been n arrivals. Now, under this information, the n arrival times, remember in the previous problem, since there was just one arrival, we were trying to find the distribution of that arrival time, but now there has been n arrivals. So, we are now trying to find out the joint distribution of these n arrival times, fine. So, the n arrival times S1 up to Sn have the same distribution as the order statistics corresponding to n independent random variables uniformly distributed on the interval 0 to t. So, you take n independent uniform 0 t random variables, say u1, u2, un, then what this theorem is telling you, if you are looking at this conditional distribution of S1 up to Sn, given that nt equal to n, that has, so this has this, so this has the same distribution as, so this quantity has the same distribution as u1, so on, un, where each ui is uniformly distributed on the interval 0 to t. So, each ui has uniform 0 t distribution. So, given that there has been n arrivals up to time t, the conditional distribution of S1, S2 up to Sn, the n arrival times, is same as the distribution of order statistics of n uniform 0 t random variables. So, in the previous problem we saw that if it is a single arrival, then the time of arrival is uniformly distributed on 0 to t, and now if you are looking at S1, S2, Sn, now obviously you can understand or that why that this order statistics is coming into picture, because the S1 has to be less than S2. The time of arrival of the first customer has to be less than the time of arrival of the second customer, or the time of occurrence of the first event has to be less than the time of occurrence of the second event, which has to be further less than the time of occurrence of the third event, and so on. So you see this order statistics thing comes in very naturally. So what this theorem is telling you, that given that there has been n arrivals up to time t, the conditional distribution of S1, S2, comma up to Sn is the distribution of order statistics of n IID uniform 0t random variables, right? That's what this theorem is telling you, okay? So again, you can easily see that this generalizes what we saw in the previous slide or in the previous problem, right? Okay. So now let us see the proof of it. So remember, we are interested in the conditional density or the conditional joint density of S1, S2 and so on up to Sn, given that Nt equal to n. Now in order to find that conditional density, observe that if you take 0 strictly less than S1, strictly less than S2 and so on, strictly less than Sn, which is less than t, obviously all the n arrivals should happen before time t, because you were told that up to time t there has been n arrivals, right? Like in the previous problem, the time of occurrence of the first event must be less than or equal to t, because you were told that up to time t there has been one event. Similarly here, because you were told that up to time t there has been n arrivals, so the time of or the time of occurrence up to time t there has been n events, so the time of occurrence of these events should be less than t. All these n events should be less than t, and obviously the time of occurrence of the first one should be less than the time of occurrence of the second event and so on. So you can see why we are looking at such a condition. Now for this, for given S1, S2, Sn which satisfies this constraint, the event that the time of first arrival is S1, the time of second arrival is S2 and so on, the time of nth arrival is Sn, and up to time t there has been exactly n arrivals, that is equivalent to the event that the first n plus 1 interarrival times satisfy this. Now if the first arrival is at time S1, that means the first interarrival time is S1. Now if the second arrival time is S2, that means the second interarrival time is S2 minus S1. So going like this way, since the time of nth arrival is small sn, so the interarrival time or the nth interarrival time should be Sn minus 1, but now you are also told that up to time n there has been exactly n arrivals. So between Sn and t there should not be any arrival. So let me draw a picture that should make things clearer. So this is 0, say this is S1, this is S2, so on, this is Sn, and this is t. Fine. Now so this is the first interarrival time, this is the second interarrival time and so on. Now also, since up to time t there has been n arrivals, so you know that in this interval there has been 0 events, right? Or in other words, the n plus first interarrival time should be greater than the length of this interval, which is t minus Sn, right? So why this last thing is see, the first n terms you can easily understand, because once you are told the arrival times, you can easily find out what the interarrival times are. Now you are also told that up to time t there has been exactly n arrivals, and the nth arrival happened at time Sn. So in this interval, which is from Sn to t, there has been no arrival. That means the n plus 1th interarrival time is greater than t plus Sn, because in this interval there has been no arrival or no event. So the n plus 1th interarrival time should be greater than t minus Sn, because remember what was n plus 1th interarrival time? That is basically the time between the nth event and the n plus first event. You know the nth event happened at time Sn, and up to time t the n plus first event has not happened. So the n plus first interarrival time should be greater than t minus Sn. Fine. So you see that this now this event, that the first arrival time the first event happened at time s1, the second event happened at time s2, and so on. Nth event happened at time Sn, and Nt equal to n, that is equivalent to these conditions on the first n plus 1 interarrival times. And once we get condition, like why are we trying to get conditions, equivalent condition in terms of interarrival times? That is because it is very easy to deal with interarrival times because they are independent and identically distributed. The arrival times are don't have such easy structure that of independence and identically distributed, but if you look at the interarrival times, they have a much simpler or easy to deal with structure, namely IID structure. So that's why we converted the event in terms of arrival times to we converted it into an equivalent event in terms of interarrival times, right? Now, once you observe this thing, now it becomes very easy to find the conditional density that we are trying to find. So since the interarrival times are IID with exponential lambda, so we are assuming that it is a Poisson process with rate lambda, the conditional density of S1, S2 and so on up to Sn given Nt equal to n is this quantity. Let me clean it up a bit. So remember, so this we are trying to find out the conditional density. So this you can think of as this exactly, that S1 equal capital S1 equal to small s1, capital S2 equal to small s2 and so on, capital Sn equal to small sn given that Nt equal to n. That is the conditional density. Now again, if we use the formula of conditional probability, so this conditional density should be this event, that S1 equal capital S1 equal to small s1, capital S2 equal to small s2, capital Sn equal to small sn, and intersection Nt equal to n divided by probability of Nt equal to n. So that should be the conditional density. But now once we have observed this fact that this event is equivalent to this event, so now see, this is basically the probability that T1 equal to S1, this is the probability that T2 equal to S2 minus S1. Again, so this is slightly heuristic because these are all continuous random variables, so I'm writing just the density, but the density is not actually probability. But again, this heuristic very much works in most of the situations. So here, this is basically, you can think of it as T2 equal to S2 minus S1 and so on. This is Tn equal to Sn minus 1, and this is the last thing, that Tn plus 1 is greater than T minus Sn. That probability is just e to the power minus lambda T minus Sn. So it's just an exponential lambda random variable taking value greater than T minus Sn, that is just equal to this, and this is the probability that Nt equal to n. Now if you do all the cancellation, you just end up with this, and we have already seen this is true if this is true, otherwise this is equal to 0. And now you can easily see that this is the density or the joint density of order statistic corresponding to like n IID uniform random variables having n IID uniform 0t random variables. Recall the density. What was, so if say x1, x2 up to xn, where IID continuous random variables having the common density small f, then the joint density of the order statistic was given by n factorial times product of the densities. So provided that in a region where like in this kind of a region, so remember what is the density of uniform 0t, it is just 1 over the length of the interval, so which is t, so n factorial times 1 over t to the power n, so you precisely get n factorial over t to the n. So just recall what was the formula for joint density of order statistic corresponding to n IID continuous random variables having common density f. So here the density is 1 over t, and hence you get that this is the density in this region. That is because we are like for order statistic, this thing has to be true. The first order statistic should be less than second order statistic and so on. And also you get this less than t, that is because here you are told that there has been n arrivals up to time t. So in this region you get this density and 0 elsewhere, and this is precisely the density of order statistic corresponding to n IID uniform 0t random variables. Fine. So we have proved the theorem. So what we have shown is that if you are told or if you are given the information that there has been n arrivals up to time t, then the conditional distribution of the n arrival times S1, S2, Sn has the same distribution as the order statistic of n IID uniform 0t random variables, right. That is the main theorem, and this theorem generalizes the problem which we solved in the first slide, where there was just one arrival, right. So if it is one arrival, there is nothing like uniform, there is nothing like order statistic. So it is just uniform. In the first slide it was just uniform on 0t, but now there are n arrivals or n events. So it is order statistic corresponding to n IID uniform 0t random variables. Fine. And why this order statistic is coming into picture? That is because of the simple reason that the first arrival time should be less than the second arrival time and so on, which should be finally less than the nth arrival time, and all this should be within the interval 0 to t. Fine. Okay. And what was the main thing that we did in the proof? The main thing was to convert the event in terms of arrival times to event in terms of inter-arrival times, and the advantage is inter-arrival times are IID having distribution exponential lambda. So once we write the event in terms of arrival times as event in terms of inter-arrival times, now we can easily write down that probability. So here basically we are writing down the density, but heuristically that is what we did. So find that way we got the conditional density. Fine. Okay. So now let us see few problems based on the concept that we just learned, namely the conditional distribution of arrival times. Fine. So let us start with the first problem. Customers arrive at a bank according to a Poisson process with rate lambda per hour. So here the unit is per hour. Suppose two customers have arrived during the first hour. So this is the information that you are given, that within the first hour, that means within 1 unit of time, there has been 2 arrivals, or there has been 2 events that you are told. Now the question is, what is the probability that both arrived during the first 20 minutes? And the second problem is at least one arrived during the first 20 minutes. Okay. So this is t. Now remember, so your rate is given in terms of hour. So 20 minutes is just 1 by 3. So here this is t equal to 1 and this is 1 by 3. So you are told that in this there has been 2 events. Now the first there has been two events on this interval of length 1. Now you are being asked what is the, so under this information, what is the conditional probability that both the events happen within this time interval of 1 by 3, right? And the second one is saying what is the probability that there has been at least one arrival in this time interval of length 1 by 3. Let us see how to solve this. Again, we will use the fact that given that there has been n arrivals up to time t, the conditional arrival times are the conditional distribution of the arrival times is same as the distribution of order statistic corresponding to n IID uniform 0t random variables. So, here n is 2, t is equal to 1, right? 2 arrivals on a time interval of length 1, fine. So, the probability that both the arrivals will happen in the first 20 minutes. Now, both the arrivals will happen in the first 20 minutes, that means so the arrivals, the conditional distribution of the arrivals is same as the distribution of order statistic. Now, both the arrivals are happening within first 20 minutes, means if I look at the maximum, that is less than 20, right? If both of them are less than 1 by 3, that means maximum is less than 1 by 3. So, the probability that both the arrivals will happen in the first 20 minutes is same as the probability that maximum of 2 independent random variables having uniform 0 1 distribution is less than 1 by 3, because you are saying that both the arrivals happened by time 1. So, you are asking the about the probability that both the arrivals happened by time 1 by 3, but that is same as the probability that the maximum is less than 1 by 3. Now, so that is same as the maximum of 2 independent random variables having uniform 0 1, 0 1, because here t is 1, distribution is less than 1 by 3, but you know how to find the distribution of maximum. So, probability that 2 max of say u1 and u2 is less than or equal to 1 by 3, but since if maximum has to be less than 1 by 3, that is same as both has to be less than 1 by 3, these are independent. So, this is just simply u1 less than or equal to 1 by 3 times u2 less than or equal to 1 by 3. So, the first one is 1 by 3 because it is uniform 0 1, second one is also 1 by 3. So, you get 1 by 9. So, the probability that both the arrivals will happen in the first 20 minutes is 1 by 9, right. Now, let us look at the second problem. So, here we are asked that at least one arrived during the first 20 minutes. Now, if we can find the probability that no one arrived within the first 20 minutes, then if I just do 1 minus that probability, that will give me my required probability. So, this is one standard trick. So, in many places in probability or in many problems in probability, if you are asked to find out at least something, you find the probability of the complement of that and then do 1 minus that probability. Again, this is a very standard trick in probability. So, here we are being asked the probability that at least one arrival happened within time 1 by 3. So, first let us try to find out the probability that no arrival happened within time 1 by 3. But what is the meaning of that? That no arrival happened within time t. That means both the arrivals happened after time 1 by 3. That means the minimum of them is greater than 1 by 3. So, the probability, so the required probability is 1 minus, so here the term, the probability is missing. So, it is 1 minus the probability that minimum of 2 independent random variables having uniform 0 1 distribution is greater than 1 by 3. So, if both the arrivals has to happen after time 1 by 3, that means the minimum is greater than 1 by 3. That means the minimum of 2 uniform 0 1 random variables is greater than 1 by 3. If we can find that probability, then the probability that at least one arrival happens within time 1 by 3 is just 1 minus that probability. That is precisely what we have done here. Now, again, since we have 2 independent random variables, the probability that the minimum of them is greater than 1 by 3 is just that each of them is greater than 1 by 3. These are independent. So, it is just probability that the first random variable is greater than 1 by 3, and again probability both of them are greater than 1 by 3. So that is just 1 minus 1 by 3 whole square. That is because the distribution is uniform 0 1 and they are independent. The whole square is coming because of independent, and 1 minus 1 by 3 is coming because both of them has uniform 0 1 distribution. So the probability that a uniform distribution or a random variable having uniform distribution takes value, uniform 0 1 distribution takes value greater than 1 by 3 is 1 minus 1 by 3. Now this has to be true for both the uniform random variables. So you get 1 minus 1 by 3 the whole square, and now you have to do 1 minus because you are actually asked about at least one arrived during the first 20 minutes, but what you calculate by 1 minus 1 by 3 whole square is none of them arrives within the first 20 minutes. So if you do 1 minus that, you get the required probability. So finally you end up with the answer 5 by 9. So the probability that at least one of them arrived within time, within the first 20 minutes, you get it to be 5 by 9. And how do you calculate? You calculate it as 1 minus the probability that none of them arrived within the first 20 minutes, and that probability is just simply the minimum of two independent uniform 0 1 random variables is greater than 1 by 3, and that is just 1 minus 1 by 3 whole square. Fine. So that's the very simple idea. So you see, this problem was very simple. In one case, you needed to find out what is the probability that maximum of two independent uniform random variables is less than or equal to 1 by 3, and in the other problem you needed to find out that the minimum of two independent uniform 0 1 random variables is greater than 1 by 3. So you see, once you have the theorem that the conditional distribution has the same distribution as the order statistic of uniform distribution, then solving these problems becomes very, very simple. Fine. Okay. So the previous problem was a very simple problem. Now we look at a slightly more difficult problem. So suppose insurance claims arrive at an insurance firm according to a Poisson process with rate lambda. So you know about insurance claims. So suppose there is an insurance firm which sells insurance and claims come according to a Poisson process with rate lambda. Fine. Now the successive claim amounts are independent random variables having mean mu. Now each claim that will have an amount, what is the claim amount? Now you are told that each claim is independent and the mean is, or the average size of the claim is mu. Fine. And also the size of the claim is independent of the time of arrival of the claim, right? If I tell you when the claim has arrived, that doesn't tell you anything about the size of the claim or the amount of the claim. So the claims have are IID, and again the problem does not specify what the actual distribution is, but it only just specifies what the mean is. But for the problem that will be enough. Fine. Now let SI and CI denote respectively the time and the amount of the ith claim. So SI is the time of arrival of the ith claim and CI is the amount or size of the ith claim. Now I define dt to be equal to I running from 1 to nt e to the power minus alpha SI times CI. So this is basically the discounted, or rather total discounted claim up to time t. Now why do you do this discounting? That is because of the fact that there is some time value of money. If something is worth 100 rupees today, that is not worth 100 rupees say 1 year from now, because if you invest this 100 rupees in a bank or a post office, that will grow to something more. So there is what is called time value of money, or something that is worth 100 rupees in future is not worth 100 rupees today, it is less, right? So there is what is called this time value of money. So if you are going to get some payment or some amount in future and you are trying to analyze it today, so you'll have to discount it, or you'll have to you'll have to bring in the fact that there is this concept of time value of money, because if you invest money today, it will grow in future, like it will increase in a future date, right? Because of that, we are doing this discounting, right? This is just for time value of money. So this is the total, because you are doing the analysis today, but the claims will come in future. So basically, say from the insurance firm's point of view, this is very important to know, say up to a time t, what will be the total amount of claim that will arrive. But again, because you are doing the analysis today, so the future claims you'll have to just discount it because of the fact that there is something called time value of money. So this is the total discounted claim that arrives up to time t. So again, this is a very important quantity from the insurance firm's point of view. Fine. Now the question is, find expectation of dt, or the average of dt, average total discounted claim which will arrive up to time t. Fine. So you can easily understand that such a thing is very important from a insurance firm's point of view. So again, this is a very real life problem. Okay. Now how to do that? Now we are interested in, we want to find out expectation of dt. Again, we will use the trick that we have used so many times in this course before, and which is used many times everywhere in probability, which is this trick of conditioning. So expectation of dt is expectation of dt given nt equal to n times probability nt equal to n. So this is just probability nt equal to n, and then you sum over n running from, sorry, it is not sum from n, it should be sum from 0. Fine. N running from 0 to infinity, because nt is a Poisson random variable, so it takes values from 0 to infinity, right? So we find the expectation by conditioning on the number of arrivals up to time t. Fine. So first, so in order to find this, now we already know what probability nt equal to n is, so we need to find out what this quantity is. Fine. For that, let us denote by u1, u2 up to un n IID random variables with uniform 0t distribution. Again, from where this is coming, that is because you are conditioning on the fact that there has been n arrivals up to time t, or n events up to time t. Now we want to find the conditional expectation of dt given the event that nt is equal to n, or given that there has been n arrivals, n events up to time t. Now recall the expression for dt. So we have just written down that here. Now since nt equal to n, this quantity is basically equal to expectation of summation I running from 1 to n, because now you are given that nt equal to n, e to the minus alpha si times ci given nt equal to n. Fine. But now given that nt equal to n, you know what is the distribution of si, that has the same distribution as the ith order statistic of n independent and identically uniform distributed uniform 0t distribution. So again, here we are using the theorem that we learned in the second slide, right? So now, and CIs are independent of all this, because CIs are independent of the arrival times. So this SI I can replace by UI, and also now, so in this case I couldn't push the expectation inside the sum because this NT was also a random variable, but now NT is equal to n, so I have replaced NT by n, so this just simply becomes equal to this, right? So there are many things that I am doing here. So first I am plugging in NT equal to n, that is because it is given that NT equal to n, and also the conditional distribution of S1 up to Sn given that NT equal to n is same as the distribution of order statistic of n uniform 0t random variables. So that's why, since we are interested in expectation, I have replaced SI by UI, and then I have just pushed the expectation inside the sum, because now the sum is a deterministic sum, and now this condition will vanish, because now I have already used the fact that under this conditioning SI has same distribution as UI. Fine. Now you know that these CIs are independent of these UIs, because that is because of the fact that CIs are independent of the arrival times. Fine. So this expectation will just become expectation of e to the power minus alpha UI times expectation of CI. That is because if two random variables x and y are independent, then expectation of xy is expectation x times expectation y. So that we are using here. Now expectation of CI is equal to mu, that is given. So that just comes out because it is constant. So I take that out of the summation. So you get this is equal to mu times I running from 1 to n expectation of e to the power minus alpha ui. So here I am using the fact that the size of the claims are independent of the time of arrival of the claims. So expectation of this just becomes expectation of e to the power minus alpha ui times expectation of ci, and you know that expectation of ci is equal to mu for each I. So it comes out of the summation as a constant. But now see whether, so when you are doing sum of some numbers, the order does not matter. See, 1 plus 2 plus 3 is same as 1 plus 3 plus 2 is same as 1, say 2 plus 1 plus 3. So the order in which you are doing the summation does not change the actual sum. So this sum, so this is basically you are looking at the sum of the order statistics, but this sum is same as this sum, right? Because these terms are just a rearrangement of these terms. Fine. This each, so if I look at, so here this sum is of e to the power minus alpha ui, but here this e to the power minus alpha ui without the bracket is just a rearrangement of these terms, and since summation does not depend on the order, like 1 plus 2 plus 3 is same as 1 plus 3 plus 2, which is same as 2 plus 1 plus 3, and so on. So this sum is actually equal to this sum. So the difference here is, now I have removed the bracket because both these sums have the same terms, same number of terms and exactly the same terms, only the ordering is different, but the ordering does not change the sum, right? That's what we have used to come from this step to this step. But now again this each ui is identically distributed uniform 0t random variables. So the sum, this sum will be n mu over t times integration 0 to t e to the power, sorry, not lambda but alpha. So e to the power minus alpha x dx. So mu is there, since each of these expectations is same, you get a n, and then you just find expectation of one term. So remember ui has uniform 0t distribution, so it has density 1 over t on the interval 0 to t. So and you are trying to find out this expectation, so this t comes out and it just becomes integration 0 to t e to the power minus alpha x dx. So this lambda is a typo, it should be e to the power minus alpha x dx, and now if you just do the integration, you get n mu over alpha t 1 minus e to the power minus alpha t. So we have calculated this term. So this is where we have used all we have used the fact that the conditional arrival and the conditional distribution of the arrival times given of the n arrival times, given that there has been n arrivals up to time t, has the same distribution as the order statistic of n IID uniform 0t random variables. And in other steps we have used the fact that this size of the claim is independent of the time of arrival of the claim. So that is another thing we used. And one last thing that we used is that if when you are summing up some numbers, the order doesn't change. If you reorder those numbers, the sum does not change, or the sum is independent of ordering of numbers, right? Okay, so using all this we get that this expectation of dt given nt equal to n is this. So finally, we are interested in expectation of dt, which is equal to n running from 0 to infinity n mu over alpha t 1 minus e to the power minus alpha t times this probability that nt equal to n. Now this whole thing, this thing, this thing and this thing does not depend on n, so it comes out of the summation. So what you get is just mu over alpha t summation n running from 0 to infinity n e to the power minus lambda t to the n over n factorial, but that's just simply the expectation of a Poisson random variable with parameter lambda t. So this is nothing but, we know that the expectation of a Poisson random variable with parameter lambda is just lambda. So here the parameter is lambda t. So the expectation is lambda t. So you just, this is equal to lambda t. So again this term is also there, that 1 minus e to the power minus alpha t. So now this lambda, so this t and this t gets cancelled, and finally you get this answer. So things which are not dependent on n comes out of the summation, and then you just notice that the summation is nothing but the expectation of Poisson lambda t distribution, so which is equal to lambda t, and you just then do the required cancellations and you end up with this answer. So expectation of dt is lambda mu over alpha times 1 minus e to the power minus alpha t. So you see we have calculated. So initially it looked this kind of a complicated expression, but you see the first thing we do is we condition on the number of arrivals up to time t, and once we do that conditioning, then we use the fact that given that there has been n arrivals up to time t, the conditional distribution of the arrival times is equal to the distribution of order statistic of n IID uniform 0t distribution. So that we use in order to calculate the conditional expectation of dt given nt equal to n, and then we use some small other elementary facts like that sum of numbers doesn't depend on the order of the numbers, and also we use the fact that the size of the claim is independent of the time of arrival of the claim. Using all this we calculate expectation of dt given nt equal to n, and then we again plug that in the original formula that expectation of dt is sum over n running from 0 to infinity expectation of dt given nt equal to n times probability of nt equal to n, and then we just do the algebraic manipulation and finally we get the answer, right? So again the main idea behind this problem is this conditional arrival times, fine, which we learned in today's lecture. So we have solved two problems using this concept. The first one was relatively simple, the second one was slightly longer, not difficult, but I will say slightly, the solution was slightly longer, but again the central idea is this distribution of conditional arrival times given that there has been n arrivals up to time t. Fine? Okay, so we will stop here today. Thank you all.